A black hole begins where a massive star ends. When a star far larger than our Sun runs out of fuel, gravity takes over. The star collapses inward, compressing all of its mass into an impossibly small point. This is the singularity, a place where density becomes infinite and the known laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing can escape, not even light. To an outside observer, anything falling toward a black hole appears to slow down, eventually freezing in time just outside the event horizon. But from the object's own perspective, it plunges inward without pause, disappearing into the dark. This warping of time is more than just a trick of perspective. It's a consequence of the black hole's intense gravitational pull. Despite their reputation, black holes are not cosmic vacuum cleaners sucking up everything around them. Their gravitational influence works like any other massive object, strong up close but diminishing with distance. A black hole with the mass of our Sun, placed where the Sun is now, wouldn't pull Earth in. Our planet would continue orbiting as always, just in the dark. When black holes do consume matter, the process is anything but silent. Gas and dust caught in the gravitational grip form an accretion disk, spiraling inward at nearly the speed of light. Friction within this disk generates enormous heat, lighting up the region around the black hole. This radiant energy can outshine entire galaxies, creating what we call a quasar. Some quasars are so luminous they can be seen from billions of light years away. Black holes come in different sizes. Stellar black holes form from dying stars and typically contain a few to dozens of solar masses. But at the center of nearly every galaxy lies a supermassive black hole, weighing millions to billions of times more than our Sun. The black hole at the heart of the Milky Way is known as Sagittarius A star, with a mass of over 4 million suns. It's quiet now, but in the distant past, it may have been a ravenous engine of radiation, shaping the galaxy's formation. The origin of supermassive black holes remains a mystery. Some theories suggest they grew slowly, feeding on gas and merging with other black holes. Others propose they formed rapidly in the early universe, emerging from dense clouds of primordial matter. Whichever path they took, their presence today is a cosmic anchor around which galaxies revolve. Sometimes, black holes meet. When two galaxies merge, their central black holes spiral toward one another in a gravitational dance. As they draw closer, they stir the fabric of space itself, generating gravitational waves. These ripples in space-time travel at the speed of light, stretching and compressing the universe as they go. In 2015, scientists detected gravitational waves for the first time, a collision between two black holes over 1 billion light-years away. Gravitational waves have opened a new window into the universe, allowing us to observe events that emit no light. With each detection, we learn more about black holes, how often they collide, how massive they are, and what environments they inhabit. But black holes still hold secrets. One of the most puzzling is the information paradox. According to quantum theory, information can never be destroyed. Yet when matter falls into a black hole, all information about it seems to vanish. This clashes with the fundamental rules of physics. Some scientists propose that black holes slowly leak information back out through a process called Hawking radiation, a faint glow that causes the black hole to evaporate over trillions of years. But this remains theoretical, and the paradox persists. In 2019, for the first time in history, humanity glimpsed the unseeable. Using a planet-wide array of radio telescopes, scientists captured the silhouette of a black hole in the galaxy M87. What they saw was a glowing ring of light, photons bent by gravity, surrounding a dark central shadow. This was not science fiction, but direct visual evidence of a black hole's event horizon. Today, black holes are more than just cosmic curiosities. They are powerful tools in the study of gravity, time, and the fundamental nature of reality. As we build more sensitive instruments and refine our theories, we may one day understand what lies beyond the event horizon and what role black holes play in the ultimate fate of the universe. Until then, they remain sentinels of mystery, dark, silent, and endlessly fascinating. The concept of black holes isn't new. The earliest hint came in the 18th century, long before Einstein, when English natural philosopher John Michell proposed the idea of a dark star, an object so massive and compact that even light couldn't escape it. In 1796, French mathematician Pierre-Simon Laplace echoed a similar idea. But without a solid framework for gravity and light, these ideas remained speculative. Everything changed in 1915 when Albert Einstein published his general theory of relativity. It redefined gravity not as a force, but as the curvature of space-time. Shortly after, German physicist Karl Schwarzschild discovered a solution to Einstein's equations that described a point of infinite density, what we now call a singularity, surrounded by an invisible boundary, the event horizon. For decades, black holes were treated more as mathematical oddities than real celestial objects. Even Einstein himself doubted they could actually exist. It wasn't until the 1960s and 70s that black holes gained scientific credibility. Astrophysicist John Wheeler coined the term black hole and helped bring the concept into mainstream physics. Around the same time, physicists like Roger Penrose and Stephen Hawking made breakthroughs that showed how black holes could realistically form from collapsing stars. Hawking also made a startling discovery in 1974. Using quantum mechanics, he theorized that black holes aren't entirely black. They emit a faint stream of particles, now called Hawking radiation. This means black holes can eventually evaporate over unimaginably long timescales. A black hole the size of a mountain would take longer than the current age of the universe to fully disappear. Larger black holes would take even longer. This led to a deeper question. What happens to the information carried by matter that falls into a black hole? If the black hole eventually vanishes, where does that information go? This is the core of the black hole information paradox, a tension between quantum mechanics and general relativity that physicists are still struggling to resolve. Some believe the information is encoded in the event horizon itself, or slowly released through Hawking radiation. Others argue for exotic ideas like holographic principles, or even that our universe is part of a larger, information-preserving system. In recent years, black hole science has leapt forward thanks to new technology. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected dozens of black hole mergers since its first in 2015. These discoveries have not only confirmed predictions, but revealed systems we didn't expect. Black holes more massive than we thought possible, spinning rapidly, colliding in environments like dense star clusters. In 2022, The James Webb Space Telescope launched, offering even greater power to peer into the hearts of galaxies and the early universe. Webb may help us understand how the first black holes formed and how they influenced the growth of galaxies shortly after the Big Bang. Looking ahead, the next generation of observatories, like the Einstein Telescope and the Laser Interferometer Space Antenna, LISA, will open up the low-frequency range of gravitational waves, letting us observe the slow, quiet collisions of supermassive black holes in deep space. And with projects like the Event Horizon Telescope refining their techniques, we may soon get even sharper images, not just of M87's black hole, but of Sagittarius A star, our own galactic neighbor. There are also bold theories on the frontier of science. Some physicists think black holes could be portals, wormholes connecting distant regions of space, or even parallel universes. Others suggest that inside a black hole lies the seed of a new universe entirely. And with projects like the Event Horizon Telescope refining their techniques, we may soon get even sharper images, not just of M87's black hole, but of Sagittarius A star, our own galactic neighbor. There are also bold theories on the frontier of science. Some physicists think black holes could be a bubble of space-time, disconnected from our own. We don't yet know where these ideas will lead, but what's certain is this: black holes, once dismissed as theoretical oddities, have become one of the most active and exciting fields in modern astrophysics. They connect the smallest scales of quantum mechanics with the vast architecture of the cosmos. From the explosive death of stars to the collisions of galactic titans, from time dilation to information paradoxes, black holes challenge our understanding at every level. They are not just celestial bodies, but natural experiments, testing the limits of physics itself. And as we continue to explore them, we're not just studying distant phenomena, we're learning about the fundamental nature of space, time, and our place in the universe.